Hi everyone, welcome to this week's Crunch seminar. Today we have one speaker. Today, Katayoun Eshkofti would be presenting her work on Vanishing Stacked-Residual PINN for state reconstruction of hyperbolic systems. Katayoun has been a postdoctoral fellow under the supervision of Matthew Barrow and Henrik Sandberg in the Division of Decision and Control Systems at KTH Royal Institute of Technology in Stockholm since 2024. She holds a PhD in Industrial Engineering from Ferdowsi University of Mashhad, where she was recognized as a top researcher. A thesis titled Development of a Novel Approach Based on Physics-Informed Neural Network for the Solution of High-Order Coupled Partial Differential Equation Systems introduced new pin structures applied to industrial and mechanical problems, resulting in the publication of 5 research papers in JCR Q1 journals. Her current projects focus on the development of predictive maintenance algorithms for wastewater pump stations, as well as advancing pins for real-world problems in control. With a short introduction, I now invite Katayoun to present her work.
Okay, thank you for the introduction. I would also like to thank Professor Karniadakis and my dear Nazanin, and also the Crunch group for the invitation. I'm truly honored to present at the Crunch seminar for the second time, and I already looking forward to the third one. So my talk today is about our recent publication in IEEE Control Systems Letters titled Vanishing Stacked Residual PINN for State Reconstruction of Hyperbolic Systems. Which was done in collaboration with and under supervision of my postdoctoral supervisor, Matthew Barrow. We are also working on extending the structure to make it more sophisticated and more intelligent. So to cut it short, I'd like to give a roadmap of this presentation. I'll start with the motivation, explaining why solving the hyperbolic PDEs is both important and challenging. And then I'll introduce the concept of hyperbolic PDEs and vanishing viscosity, which provides a foundation for handling discontinuities. And next, we will see why vanilla pins fall short and what limitations arise when directly applying them to these problems. So after that, I present the idea of a single residual block and then extend it to the full vanishing stacked residual pin. And subsequently, I go over the experimental setup that we did and the results, and we compare different architectures. And at the end, I wrap up with the conclusion and future studies. So let me start by explaining the motivation behind this work and the challenges we are addressing. We focus on quasi-linear hyperbolic PDEs, which we all know that they play a very significant role in modeling real-world systems such as fluid dynamics, electrical energy transportation, and traffic flow. And a well-known example here is the Hamilton-Jacobi equation, which appears in optimal and predictive control. This shows us how hyperbolic PDEs are not just mathematical objects, but tools that drive practical applications in control and optimization. So one of the important challenges is state reconstruction, and by that I mean we should estimate the full evolution of the system even when we only have access to partial and noisy measurements. So in order to do this, it is super important. We know that this is super important for monitoring distributed systems and ensuring effective control. So the difficulty in system identification and reconstruction arises from many factors, and to name them, they are nonlinear dynamics, discontinuities, non-uniqueness, and even infinite dimensional complexity. We have the traditional model-based approaches, but we know that they require very precise models and theoretical guarantees. So these are rarely available in practice. And the standard machine learning approaches demand huge data sets and risk overfitting. So we try here to integrate some novelties from machine learning and physics-informed neural network to address this issue. I know you are all very familiar with this type of problem, but I would like to clarify which specific problem I'm focusing on. So let's look at the mathematical problem that I'm focusing and we are dealing with a one-dimensional quasi-linear hyperbolic PDE, as you can see. And the main goal of this work is to find the solution U to the PDE that is shown here. And it is defined over a spatiotemporal domain. We specify initial condition and boundary condition at both ends. And the flux function is assumed to be smooth, at least twice continuously differentiable and globally Lipschitz. So these conditions guarantee that the PD is strictly hyperbolic and the mapping remains bounded. So on the right, you can see that you see a Berger's-like equation, which is a prototypical example of this class of PDEs. And I should mention that this solution has both smooth regions and sudden jumps that are marked. And these jumps represent shocks which naturally appear in nonlinear hyperbolic PDEs. So this irregularity means that the solution is not smooth and the standard approximation theorems may not hold. But I need to mention that the smoothness is not the only difficulty here. So if we dig deeper into one of the core difficulties with quasi-linear PDE, we can see that the issue is multiple solutions. The problem is that when discontinuities appear, such as shocks, the PDE might admit multiple possible solutions. So this is a big problem because in applications, we need a unique, physically meaningful solution. So on the left, you see one mathematically valid solution, and on the right, you see another one. Both satisfy the PDE, but clearly they behave very differently. So how do we choose the correct one? The answer is we need an additional condition, which is known as entropy condition. So this ensures that shocks follow the physically admissible direction. So this means that the entropy flux must satisfy a pointwise inequality that is shown in here. And without this entropy condition, the PD is not well posed. So because we have multiple solutions. So with this condition, we can identify the unique physically relevant solution. To resolve this issue of multiple solution, one of the powerful approaches is to use what is called vanishing viscosity. So the idea is to modify our PD by adding a small viscous term, as you can see in here, where gamma is greater than 0. So when gamma is equal to 0, we are back to the original hyperbolic PD. But when it is greater than 0, even if it is very small, the equation becomes parabolic. So this small change makes a big difference. With viscosity, the PD admits a smooth solution, and it also guarantees uniqueness. So instead of having many possible solutions, the viscosity term selects the physically meaningful one. So on the left, where gamma is equal to 0, we see the original hyperbolic solution with shocks and discontinuities, and on the right with gamma, yes, here, with gamma that is very small, we see that the original hyperbolic solution, the sharps jumps are smoothed, and we can see the effect of viscosity. So we gradually let gamma reaches to 0, and the viscous solutions converge to the vanishing viscosity solution.
Can I
which
ask you a
corresponds-
question?
Yes, yes.
Yes. So if I look at the lower line at x equals 0, the solution changes completely. Why? You see at x equals 0 on the right is red, but with gamma equals 0 is green.
Okay. Sorry,
Here. I'll point out around there. The solution changes with gamma, and for gamma equals as gamma.
Because here we set the gamma to 1000. It reaches to 1000. Yes, okay. Oh, you mean here?
Yeah, it was the last one that you showed. It was.
Yes, this is the last one.
No, gamma was 0.005. There is a diffused red region on the bottom side of the previous slide.
Right. There's a diffusive region which is different value from.
If you go one slide behind, Katayoun.
Yes.
Yes, I think this was what.
Yeah.
Mm-hmm. Okay, so can you please ask your question again? Because
I think you're developing a boundary layer. You're developing also, if you look at the top, you're developing the introduction of gamma being parabolic. Now you're developing boundary layers, which are unwanted for this problem because it's a finite domain. But anyway, maybe we can discuss it later. Don't worry about it.
Okay. Okay. Yes. So should I continue right now?
Yes, please.
Okay. So this vanishing viscosity methodology gives us this practical way forward. So instead of approximating the possibly non-smooth entropy solution, we approximate the smooth viscous solution U gamma using physics-informed neural networks. So the vanishing viscosity approach not only enforces us to uniqueness, but also makes the problem more amenable to physics-informed neural network-based approximation. So I'll show how we incorporate this into our framework. Okay, so up to here, we've seen that how vanishing viscosity can help us define the correct solution. But if we want to approximate the solution with a standard PINN, some difficulties immediately appear. So here the optimization problem is defined as finding the best neural network parameters by minimizing the total loss. The loss has two components, loss of data, which are the measurements, and we want to measure how well the network fits the available data, and we have the loss of physics, which measures how well the network satisfies the PDE itself. So the problem is that for hyperbolic PDs, this vanilla PINN setup doesn't work reliably. It has two reasons. First of all, we saw that we can have multiple solutions, and the PINN loss doesn't tell the network which one is the correct one. So second one is that the method only works when the PD operator is Lipschitz continuous. which unfortunately is not the case for hyperbolic problems with shocks and discontinuities. So vanilla pins are not enough here, so we need a refined version that can handle shocks. So in the next step, we introduce another structure for the pin, which is which has a refinement step and uses a residual block. So the idea is to start with a baseline pin, which we can see in here. And this gives us an initial approximation U hat 0 of the parabolic PDE with viscosity. And this ensures smoothness and entropy compliance. And at the second stage, we refine this approximation by adding a correction term represented here as a residual network. And this means that U hat gamma 1 equals the baseline pin prediction U hat 0 plus a small correction controlled by alpha 1. So here you can see the flow. So we use the previous output and feed it to the next pin structure. So the new optimization objective involves both sets of parameters, theta 0 and theta 1, plus the correction weight of alpha 1. And this loss function combines the initial viscosity-based approximation with the refined solution. So this approach helps us to reduce the likelihood of multiple non-physical solutions, and also it decreases the magnitude of shocks and making the approximation more stable and realistic. But we want to extend our idea to vanishing a stacked residual pin because a single residual block already improves stability, but might fail when we have very large and sharp or localized features. So the idea is simple. Instead of correcting the baseline pin once, we apply multiple correction stages in sequence. So at each stage, the solution U hat I is built from the previous approximation plus a small residual correction scaled by alpha I. So the approximation gets progressively refined stage by stage. So you can see, So you can see in the this schematic that the input first passes through the baseline pin and giving U hat 0, then each residual pin improves it slightly, U hat 1, U hat 2, and so on, until we get the final refined solution. So an important detail is that the viscosity parameter gamma decreases across the stages, and this follows the vanishing viscosity principle. In our paper, we use this superlinear viscosity term, and we considered P equal to 2. And we start with a larger viscosity for stability, and then gradually reduce it so that the final stage capture the sharp hyperbolic behavior. So the optimization now involves all parameters, theta I and alpha I, and the total loss is an average of the physics-informed losses across all the stacked layers. So each block is trained to contribute meaningfully while keeping correction small and consistent. So we go from parabolic approximation to a fully entropic hyperbolic solution. So if I want to summarize this slide, the vanishing viscosity residual PIN combines the best of both worlds, stability from viscosity and flexibility from stacking. So in the next slide, I'll show you how this performs in practice. In order to test it and implement it, we use the traffic flow modeling. So the goal here is to estimate vehicle density along a road segment using only local density measurements. And we use the LWR model. So in this setup, the density U is normalized. So U, when U is equal to 0, it means that the road is empty. And when it is equal to 1, it means that it is a bumper-to-bumper condition. So we consider this flux function. And this is a well-grounded green shield flow equation which relates vehicle speed and density. And because this flux is nonlinear, shocks and discontinuities can naturally appear in traffic density, which make it challenging for the problem to learn the solution. So to apply our method, we add a small viscosity term starting from 1/10 and then test different numbers of stacked residual blocks. For the measurement, for the data measurements, we use simulated density from Godunov simulator. And in the next slide, I show you the results that we obtained from 5 different variants of PIN. So we have the vanilla PIN and the viscosity, adaptive viscosity, the baseline stacked PIN, modified stacked PIN, and our proposed method. So for the stacked architectures, we defined the baseline PIN consists of 3 hidden layers with 30 neurons, and each residual correction block contains 3 hidden layers with 40 neurons each. And in order to have a fair comparison, vanilla PIN and adaptive viscosity, which are single stage structures, we considered 9 hidden layers for each one with 14 neurons. And we trained them for 15,000 iterations, but with LD stopping criteria. So we use the relative error to measure performance. And as you can see, this proposed method can improve the accuracy about an order with respect to vanilla PIN. And also, if we look at the mean squared error for 20 independent simulation, we can see that the vanilla has the largest error here, and the variability and baseline stacked improve stability, but the vanishing stack residual PIN consistently achieves lowest error. So these experiments can show us that the vanishing stack residual PIN is not only more accurate, but also more robust and stable compared to other standard or modified architectures. And to better understand how the method works, we can see at the left side, we have the true density of the traffic flow over space and time, and high values correspond to the congested regions, and low values represent free flow. And in the middle, we show the error between the predicted solution after 3 stack layers, you had 3, and the true solution. And I also want to attract your attention to the fact that the errors are relatively small. And on the right-hand side, you see the residual correction term, alpha 1, with the neural network related to that layer. This highlights that the residual block specifically targets those sharp transitions and shock regions. So I think and I believe that our method learns to focus on the difficult parts of the solution and simultaneously tries to keep the overall approximation consistent with the true dynamics. And to conclude my presentation. If I want to refer to the main points, we propose the vanishing stacked residual PIN as a new way to reconstruct a state of hyperbolic PDEs, and by progressively enhancing the approximation through residual stacking and vanishing viscosity, we try to effectively capture discontinuities and shocks. And when it is applied to traffic density reconstruction, we saw an order of magnitude improvement in accuracy compared to vanilla PIN. So looking forward for our future research, we want to extend it to higher dimensional and more complex PDEs, which will allow us to tackle wider spectrum of applications in control and also in optimization. And yes, that was my presentation, and thank you for your attention.
Thank you, Katayoun, for the nice talk. We can now open the floor for questions. Kyle has a question.
Yeah, hi, Katayoun. Thank you
Hi.
very much for the talk. It's a very interesting idea. I have one question about the details for the architecture of the residual PIN that you have used in
Okay.
your stacked framework. So if you go to
Yes.
slide 7, I'm looking at this equation for the approximation at ith stage. So the N here is the neural network for the residual PIN, right? On the in the red box, approximation at ith stage. So the
In the
yeah, this one.
here
This is
you mean yes?
yeah. Yeah. So
Yes. Okay.
yeah. So I just wonder. So this neural network takes in the previous network solution u
Yes.
I minus 1 as its input, and also the coordinates t and h. So is it more like a neural operator thing where it takes in a function as its input and output another function?
Actually, no, not it's not like a neural operator, but I think that yes, we can extend it. I mean, we can extend it, but we get the solution. We get the solution from the previous layer.
Yes.
So it's gonna reinforced with the previous layer. I mean, with lower fidelity data. Yes, we can see that.
Right.
But we want to get to higher fidelity data. So gradually we get higher fidelity data.
Yeah, makes sense,
Yes.
makes sense. And the architecture you use here is just a simple neural network, a simple fully connected neural network.
Yes, it is fit for our neural network. Exactly.
I see. Yeah, thank you very much.
Of course, thank you for your question.
Maybe I could ask a follow-up on the first question Kyle asked. So if I understand correctly, the input to the residual, the U is corresponding to the query given to the baseline pin on the first level, right?
Yes, okay.
So typically in a neural operator, I assume you give the entire function, the entire spatial domain together as the input. Here, the input is just the value of that function at that specific query point. So hence the difference with the neural operator. Kyle? Yeah.
Yes.
Do you have more questions for the author?
Yes,
Speaker?
I have one question. This is my name is Jerome Dabon from Brown. You mentioned in the conclusion that you plan to go to higher dimensions, controls, and so on. Do you have preliminary results? And more specifically, did you try to learn the Hamilton-Jacobi solution?
Actually, we haven't tried it for the. Right now, we are working on extending the work by adding some curriculum learning algorithms. But yes, this is our future research, but not yet. We haven't experimented the higher dimensional problems.
Okay, thank you.
Yeah.
Okay, maybe I have maybe a follow-up question on what Professor Jerome asked. Very nice Katayoun. I'm Siavash, working
Thank you.
with George at Brown. So I was
Yes.
wondering if you have thought about the computational costs and if it's going to make sense if you go to higher dimensions. If you have any
You mean
thought about
the computational time and cost?
Yes. And if you can fit all those networks
Mm,
on memory.
You have a convergence plot we can look at. You didn't show us the convergence plots, like history of.
oh, actually, I don't have it right now. I mean, this setup, but yes, but I think yes, this could be a challenging. I mean, because we had this conversation with Raj at NSML, because maybe extending the work to higher dimensional requires more computational capacity. So yeah, this could be the case, but we haven't worked on it completely. But yes, that's a very interesting question.
Okay, thank you. I just wanted to know if you have thought about it or any comments. But thank you.
Yeah, thank you.
Hi, I have a quick question too.
Yes.
Yeah, that was a great talk, by the way. My question
Thank
is
you.
specifically about as we see the formulation of the loss function, do you train all the residual blocks synchronously at a time, or do you freeze the networks and then train them individually? Because otherwise, since you're having a rollout where you are using the output of the previous neural network solution for predicting the next one, don't you think that optimization problem could be a little unstable?
Yes, this is the case, and actually we are working on this problem that we kind of add this mechanism of curriculum learning by considering like a gate. So when we are training one stack layer, which is a pin, and we consider a threshold to be acceptable, and then the training goes to the next stack. So we are working on it. But right now, the whole training is done simultaneously. It's not doing part by part.
Got
So
it.
yes, yeah.
Okay,
But,
yeah, that answers my question. Thank you.
Yeah, sure.
Thank you, Ritvik. Do we have more questions for the speaker? In that case, I have two questions. So the first question is related to what Siavash asked earlier. So he asked about higher dimensional problems, but my question is about the same system that you right now considered.
Okay.
Why did you choose 3 additional stacking networks? How much will the error decrease if you used one more? Do you have the convergence
yes.
of this error with respect to number of stacking layers?
Very good question. Actually, we experimented it on several stack layers. So we started from a 0 stack layer, which is vanilla pin, and we continued until 1, 2, 3, up to 4, up to 5. And from 3 to 5, we didn't see very much improvement. So we stopped at 3.
Okay.
Yes.
Okay. But since in all this experiment, since you tried to maintain the number of neurons and number of layers more or less the same, I assume the computational cost would be similar. It wouldn't be. It wouldn't increase by increasing the stacks, right? But as you said, the vanilla had like 9 layers. The others had fewer layers to ensure same number of parameters, right?
Yes, exactly. But I mean, you mean that by adding these stack layers, we have this situation of more complexity for the computational time and cost? So this is your question, or?
Yes, it was my question, yes.
Yeah. Actually, to be honest, these residual stacked pin requires higher computation with, in relation to other structures like vanilla pin. But these, I mean, comparing 3 stack layers with 4 and 5, it doesn't make it very
Much better.
longer.
Yeah.
Yes.
Understood.
Yes.
Understood.
Yes.
Okay. Just one more question. What do you mean by
Yes.
the modified stacked network? You had the box plots, right? Can you comment on the difference between?
Yes. That's a very good question. I'm sorry if I didn't clarify it completely. So we have this baseline stacking that has been already introduced in the paper, another paper. So in the baseline stacking, we have these stack layers, but the same problem is being solved. So there is no change in the problem. But in the modified stacked PIN, I consider this vanishing viscosity. So the problem will be changed gradually. I mean, the gamma will decrease across the layers. And yes, this is the modified version.
So then how is the modified different from vanishing stack? Since I assumed vanishing also the novelty was reducing the gamma across the stacking layers, right?
Yes, okay.
So what is the difference between modified and vanishing in that case? Vanishing stacked residual.
So in a stacked residual, we considered residual.
Right.
PIN.
Okay,
Yes.
understood. Okay.
Yes.
Okay, I understood. Thank you.
Of course. Sure.
Do we have more questions for the speaker? Okay, if not, I would like to thank Katayoun again for spending her time to explain her great work to our group. And hope you all have a great weekend, and thank you again.
Thank you.